All right, welcome back, physics students. Remember, we're talking again about this idea that we call, I'm going to go with some pink here, that we call work, right? And so, what is work? We talked about how work is anytime we have a force that causes a change in displacement, essentially. So it's a constant force exerted on an object, and it has to be in the direction of motion. So if you put a force on something and it does not move in the direction of that force, there's no work. So, for example, this is something that sometimes confuses people. If you have a planet revolving around the sun, right? Well, where's the force? Well, the force, we've talked about centripetal force, is a force toward the center. Well, where's the direction of motion? Well, at any one point, this is going to be your velocity vector right here. So look, the force this way, velocity vector this way, these are completely perpendicular to each other, which means that there's no work done on a planet by gravity revolving around the sun. There's no work at all. Why? Because the planet doesn't move in the direction of the force. So sometimes that confuses people. But remember that. What is work? Work is a force that is applied and causes something to move in the direction of that constant force applied, right? And what does that take? Well, it takes energy. So what we're going to do is we're going to look at some of our previous learning and some of our previous examples and try to figure out how this all fits in. So I'm going to go kind of fast with all this. So stay tuned and just do your best to follow along. You may have to kind of go back through and slow down. But this is a video, so you can kind of jump back if you need to. So let's look first of all at what is acceleration, because we see within work we have a change in motion, so there's clearly an acceleration because there's got to be a change in velocity, and that's going to take some time. So acceleration is a change in velocity over time. We can kind of rearrange that to figure out that a change in velocity equals an acceleration times a change in time, and we've rearranged this equation to give us a final velocity, because a lot of times what we want to know is how fast are we really going after we've added this acceleration over time. And so we could solve for the final velocity of something by rearranging this here and saying the final velocity equals the initial velocity plus the acceleration times the change of time. So all we did right here is define what velocity equals, right? Or change in velocity, and then set that equal to this, and then move the initial velocity over here. So we could also redefine that as what the time is. So that the actual time final of an acceleration is going to equal the velocity change divided by the acceleration, right? So we're going to use this equation to figure out how work fits into all these other equations. So let's go ahead and keep going with our deriving here. All right, so one of the other things that we understand that work is going to do is that work, right, is going to, because work is a force over a distance, so the work is going to cause a change in displacement, right? And so how do we get change in displacement? Well, we understand that anytime you're changing velocity over time, that's going to cause something to move in a certain direction, right? So we've talked about the area under a velocity time graph is going to equal your displacement. So if you have an initial velocity, which is a meters per second, so it's a certain amount of distance in a certain amount of time, and we're going to change that velocity. So we're going to change that, and we have over time, it's going to equal your area under your velocity time graph. So what you're going to have to actually do is you're going to have to find the area of this triangle here and add it to the area of this rectangle. So that's what we did way back in some of our earlier discussions and chapters. So we found that the change in displacement, because what we really want to know is how far did we go, right, after we had this acceleration. This acceleration is a change in velocity over change in time. So we need to add up all of the area of this graph right here. So what we talked about was that we're going to have to add that. We're going to separate this out. We're going to have the area of this rectangle plus the area of this triangle. So the area of rectangle is easy. So we just have the initial velocity times the time final. We have that. Plus 1/2 base times height is going to give us the area of a rectangle. So it's going to be 1/2 times the change in velocity, right, times the change in time, or the time final, right? So what we did, though, is we said, okay, we know that acceleration equals a change in velocity over change in time. So if I rearrange that to see what change in velocity equals, change in velocity equals an acceleration times a change in time. So we went ahead and we inserted that into there. So that brought us to this point right here. We had 1/2 times the acceleration times the time final times the time final. So we ended up with, because what we wanted is, we didn't want velocity in here. We wanted to pull acceleration into this equation right here. And so we ended up with this one right here. And so this is one that we used to solve for the final distance of things if we knew a couple of the factors. Right, and we use this equation quite a bit, and we sort of morph these in and out of each other to solve for lots of things like distance, acceleration, time, velocity, whatever piece we were missing. And so this is where we ended up right here was that the distance finally, and so all this expression is calculating the area of this graph right here. Well, then where do we go from there? All right, so from there, here's what we're going to do. We're going to take what time final equals, right, which is the change in velocity divided by the acceleration. We're going to insert that in for the time final, okay? So we're going to throw that in anytime we see time final, because we're going to get rid of time. We're going to put velocity in there. You'll see where we're going in a little bit. So what does that equal? Well, if we throw that in there, it changes all these time finals to be this, because that's what time final equals. And so here we are, right here. And so we just I just put that in there for time final. I'm going to go ahead and distribute that out, and so what we end up having is our VI VF minus VI squared divided by A, and over here it's 1/2. So we're going to have to multiply these out as well as we square the VF minus VI. So I went ahead and I did that for you right here, so you can kind of see the algebra. This is some kind of big gnarly algebra, but you should all be fairly familiar with how to do that. So if I multiply that out, I got VF squared minus 2 times VI VF plus VI squared. And so that would be the process of distributing that out right there. And if I have 1A times, or 1/2 A times that, it's going to cancel out one of those A's, and then I got the 2 on the bottom that I multiply right here. So then the next step that I'm going to do is I'm going to multiply both, all of this by the 2A to get rid of that from the bottom. Well, if I do that, it just takes away the 2A from the bottom over here, so that's gone. Multiply this whole thing times 2A, right? And so that's going to get rid of that A right here, but it's going to multiply this whole top times 2. So here I have 2VI VF minus 2VI squared. Right? And then on the other side, I have 2A, because I multiplied this whole thing by 2A to move that off the bottom. All right, so now what we can actually do is we can actually combine some things over here. We have 2VI VF minus 2VI VF, so we essentially get rid of that. That was nice. And we have negative 2VI squared plus VI squared, so we end up with just one of those, right? So we end up with one of those. So we'll put that down there, and we still have one of these, so we'll put that down there. And then if the initial distance is 0, if you're starting from rest, here's where we end up. 2 times the acceleration times the final distance equals the velocity squared minus the velocity initial squared. Velocity final squared minus velocity initial squared. So hopefully you can see how we got finally down to this point. Now, here's where the magic happens. So let's look at that. So where's work in all of this? And why have we done all of this? Well, here it is, right here. If we take force equals mass times acceleration, Newton's second law, we insert that in for acceleration, what happens is we have 2 times the force times the distance final divided by the mass. So now we've added in here force and mass. So we know acceleration equals force divided by mass, right? And so then if I go ahead and I take that and I multiply both sides by m over 2 so that I move this 2 and this m over to the other side, I have this right here. I have force times distance equals 1/2 mass times velocity final squared minus 1/2 mass times velocity initial. So this is so cool, because what do we talk about? What does work equal? Work equals the force times the distance. Well, there we are, right there. It's been in our equation the whole time. It's always been in there. And then we talked about, well, what causes work? Well, you have to input energy. Work is defined as energy. We measure it in joules. Joules is a measure of energy, right? And so the idea is work is a change in energy. In order to do work, you have to put in energy, right? And so what is energy? Well, the definition of kinetic energy, right, here we are, kinetic energy, sorry about that E, equals 1/2 times the mass times the velocity squared. And you learn this in chemistry when you learn about the kinetic molecular theory of masses. You learn about the fact that we measure the kinetic energy of gases by this right here, 1/2 mass times velocity squared. And that's what temperature is. Temperature is the average 1/2 mass times velocity squared of all the gas particles in a room. So here we are. We have the change in kinetic energy. So we could say that work equals the change in kinetic energy, right? So here's our energy right here. So energy is that force that is applied. And it is basically what goes into something. And so any system, in order to move, in order to change itself, has to have the ability to do it. And we call the ability to do that kinetic energy. And so that results in motion. And so this is basically called the Work-Energy Theorem. And so basically the idea of the Work-Energy Theorem is that work is equal to the change in kinetic energy. So hopefully this helps in getting you to understand how is it that we moved from way back in chapter 3 in the beginning of the year, from just understanding that velocity was a change in distance over time and acceleration was a change in that velocity over time, all the way down now to a simple equation, work equals force times distance. But how is that all a part of everything we've done so far? So this shows you how all of this fits together and comes together in one idea. So what's in all of this? Energy is in all of this. Work is in all of this. Distance, displacement is in all of this. Initial velocity, final velocity, acceleration, time. Everything is all in this very simple starting equation. We have acceleration, we have force equals mass times acceleration. These things right here, they all include every single thing that we have talked about and learned so far, and we're just basically unpacking it as we go. All right, hopefully that helps to understand where work comes from, where kinetic energy comes from.